Hello, my name is Melvin. We have a lot to cover today, so I'm just going to go over this quickly. This is our lab 4 oscillations. The purpose of this lab, giving our initial conditions, is to simulate a spring oscillation. We're going to compare the simulation to the real-world observations we're given to determine if the model that we made is accurate and if the relevant physics principles that we used stand true. The fundamental physics here is that the change in the system is equal to the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring energy. It's a mouthful, but the main idea is that the energy of the system will be constant, and each type of energy will kind of just jump in between forms. All of our constants for the spring force here for our evaluation of motion are thankfully given to us. On the right here are our initial conditions, just off the video, where the ball was relative to where the spring was attached. This is a preview of the results here. You can kind of see the oscillation going on over here in the energy. This is the position relative to the x-axis of the mass on the spring. It definitely starts off more consistent, gets a little bit more chaotic over here. But the y position itself here, definitely a lot more consistent. Probably the most consistent, most beautiful graph I've ever made. But yeah. Something to go over here is our system, which is the Earth, the mass, and the spring. There's not going to be any external work, which is important for our later discussions. This is relevant code. The spring constant is 6.82. That's derived mathematically from the relationship that the spring constant shares with the period of the oscillation. That's to say that t is equal to 2 pi times the square root of m over k, which when you move around, you'll get that k is equal to 4 pi squared, mass divided by the period. You can do the same thing for the relaxed length of the spring, but I'm not going to go over that because there's a lot to talk about, so just know that it's 0.123. The next portion of code here kind of just gives us relevant constants for the spring. That's the length, the orientation of the spring, and the compression or stretch. These are all our energies, so kinetic energy, gravitational energy, spring energy, and then if you combine all those, you get the total energy of the system. In our iteration, we have the force of gravity and the force of spring, because those are the only two forces working at that moment. So we just add those up to get F net. And with F net, we can update our velocity and position. With our updated position, we move on to updating the spring. Now that we have a new position, the spring has changed. We get the same constants here. It's the same stuff. New length, new orientation, new compression or stretch. And with those, we update our energy because now we're in a different spot. We got some change in kinetic energy somewhere. The change in height potentially gives us a new gravitational potential energy. We know that the length of the spring changed, so the potential spring energy will change itself. And we calculate the last E, the final E. This is like almost the final state, so you could say. And we get delta E, which is the final state E minus the initial state E. And you'll see that it's not terribly, I mean, it doesn't change a lot here. If you look at this like this, you'll see that these points cancel out, and it's almost like a constant because the energy of the system is constant. But you'll also see that the energy kind of bounces around. It'll be in the spring at some point, and then at some point it'll be in the gravitational potential energy, and then it's really cool to see actually. This is just a good visualization for that. Moving on, this is the results of the y position for the model, and it's really accurate actually. Like I really liked this part of the work. And then there's the x position, not so accurate, but it's definitely almost there. It gets worse towards the end of it, and it's probably strictly because of the experimental, not the model, but just the experiment that gives us the error. There's not an exact what if portion of this experiment, so I'm just going to use this part of the video to go over a couple points of error that I could have encountered, and that's one, the video quality. It was really difficult to tell exactly where the center of mass of the end of the spring was. I definitely had some variation on where I clicked when I was doing the tracker stuff. The video length was different as well because the frames per second were not what we were accustomed to. I think I got it right, but it's definitely a point of error for some people. And then 3, data destruction. Every time I export data from tracker, I seem to lose the first or last point. And I think that occurred here because for the y position, for the y graph here, the experimental data, if you were to translate it right, like maybe 1 or 2 points, you would have they would be exactly on top of each other. So yeah, that's it for today's lab. I hope you enjoyed. Hope you give me 100. Have a good day.